Hey guys, welcome back to Algos Explain. My name is David, and we are doing another Edabit question. I like this platform, so I think I'm going to do more of it. Definitely going to at least try to build up those playlists at the very least, and I have a good feeling I'm just going to be doing more of these anyways. Unless I get requests for leak code, then I'll pivot at one point, but I do like this platform. So this is a level very hard question, and I'm very excited about doing these tree questions. I also recorded a bit of myself doing a whiteboard, and so I'm not going to talk too much about why I'm excited for binary tree because I think I added it there. But we're going to go ahead and read over this question, and in that video, in that recording, I talk about the strategy for this particular question. So this was published by Sweet. We have two arrays, n and p, where n represents the value of a node in a binary tree and p is the parent of n. And so, okay, red flag right here, you're given arrays that have single one-letter variable names, and you know how you've been told never create variables or anything with single letters because they're hard. And admittedly, I have seen that in some of the work that I've worked with in real life, and yeah, it's pretty hard. And in this case particularly, there's no reason why it wouldn't be hard in an interview situation when the stress levels are at the very highest, you know? And so you'll see me change these variable names when I get to writing the code, but for you too, when your interviewer says, okay, I have an array called n and this is the array, because they're going to read it out to you, you don't have to just write n. You can say, okay, these are the nodes, so I'm going to call this array nodes. So anyways, we're given two arrays, which is this n and this p. And pretty much what they want us to do is we want us to take these and kind of decipher what it means to be a binary tree with this relationship. Really quickly, the relationship is this P2 is the node with the value 2 inside of it. This 2 is going to be the parent of the node that contains the 1 in it. And I draw this out visually because just talking through it is very hard to understand. And when your interviewer is also kind of giving you this question, once you have these arrays written down and maybe there's no more things that he's telling you, go ahead and draw out the tree. For binary tree and graph questions, I guarantee you drawing it out and visualizing it is the key to success. Unless you have some kind of crazy brain, which then, I don't know, you probably aren't watching this video anyways because you already have the solution for it. Also, if you haven't done these questions yourself, please go ahead. Please do it before watching my video. You know, I risk losing views, but really, if you haven't tackled these questions yet, go ahead, look in the description. The URL is right there, and go ahead and try it out at least for a few minutes. At least read the question and try to think of a solution yourself, and come back. If you can't get it, maybe even if you did get it, come back to see if we got the same solution, and maybe at that point you could just skip to the end of it or something and skip the explanation just to see if the strategy was the same or not. But anyways, I believe this ends just a reading of the instructions, or actually there's one more thing at the very bottom here. So just iterating this, the root node is at the very top, internal nodes the middle, the leaf nodes is just defined as being nodes that don't have any children. And so this 7, if it had one child, this would no longer be a leaf node, that child would be the leaf node. And so with that said, one more note down here, all values of n array are unique. That means that, well, that just means what it means. That means that you're not going to get a -8 here and a -8 here. One more thing here, this statement right here, write a function to find the node type of binary tree ordered by the value of the node. Output one of the following. I honestly read this statement a couple times, and I tried to edit it, but I don't have enough experience points. As you can see, you could suggest edit, but I don't have enough experience points on this platform yet. Write a function to find the node type of binary tree ordered by the value of the nodes. I would probably rephrase that as write a function to find the node type of the node within this binary tree, because you're pretty much given the two arrays, you know, representing the nodes and the parents, and then you're also given a node. So, you know, write a function to find the node type of the node given within the binary tree. That's that might make things a bit clearer. But anyways, let's go over to the whiteboard portion of this question now and visualize it. Hey guys, okay, so this is the part where I'm going to kind of talk about binary trees a little bit more, and we're going to take the example from the instructions portion of the problem for Edabit, and we're going to visualize it, and we're going to try to come up with a strategy to solve the question. And so this is the example that we see right on there. For some reason, or not for some reason, they just chose to put it in a column form. Of course, we're not used to seeing arrays like that, and more so, what's going to happen for you in an interview situation is your interviewer is going to be vocalizing this. They're going to say, okay, I have an array of n nodes, and they're going to start reading out numbers to you. Instead of you just standing there listening, what you have to do is you have to start writing as they're talking, because you don't want to waste time. Time is very precious, is very limited during interview situations, and if they read out the entire array for n and the entire array for p, and then they're like, okay, solve the question, and you didn't write anything down, you're going to have to ask them, of course, to read it one more time, and that's another like 30 seconds gone, which you could have used to solve the problem, or even maybe if you finished everything early, ask him questions and make yourself look good. But anyways, let's start off by talking about a binary tree. A binary tree is a very exciting topic. I'm glad that we are at this point now, or I'm glad that you are at this point now where you're starting to look at trees. Hopefully the next few questions you're going to start looking at graphs. And that is where I really think, okay, real world applications start to come in. Once you start seeing graphs, like I think the simplest way to see the application of graphs is to see like a maps app, like your navigational app. What's the fastest way to get from point A to point B? And kind of graph algorithms help with that. And to do graphs, you do trees. Trees very similar to graphs, except trees they have just less connections than graphs, and they usually just go one way. Binary trees are different from normal trees in the sense where this is a binary tree where it would have only two children, and these are the children right here, and this is the parent node or the root node, and it only goes one way. It pretty much goes down. The relationship is one way. However, sometimes the children node does know its parent node, and so in that way you might think, okay, the relationship is going that way also, but in terms of defining who's the parent and who's the child, like a hierarchy, there definitely is one. And they call it a tree even though the branches are going downwards. And so very important, binary trees only have two nodes, and these are called nodes. It's just like you could consider a node to be just an object with information in it. For our purposes, our nodes is going to be an object, or it's not an object here, but think of it as an object with a number in it. That's the only information. Sometimes it holds more information. Sometimes it holds just a simple number value, like we're seeing today. And so, and the reason why binary trees are special is because trees can't have more than one children, and so this would be just a regular tree, except we're working with binary trees. So let's erase that. All right, so let's go. We have this array here with the nodes and the parents. So let's go ahead and visualize it, make it into a tree, and then see how it's going to help us. Or once we see that, we're probably going to be able to determine, okay, what's going to be our solution for it. So we know that these correspond via index, and so if I were to draw barriers or lines right here, we can see that this 2 is going to be the parent of the 1, this 2 is going to be the parent of the 3. Right off the bat, we know that binary trees only have 2 children, and so we know that this 2 is going to be the parent of both the 1 and this 3. And then we could see here the 8 very similarly. The 8 is going to be the parent of the 6 and the 9. And we can see that as we go on, the 5 is going to be the parent of the 2 and the 8. And there's a -1 at the 5 there. I do believe that is not written in the statement or the instructions. And perhaps your interviewer is not going to tell you what the -1 means. You're going to have to ask him, okay, what does that mean? And for our purposes, the -1 represents it being the root, or the very top. And so let's go ahead and organize this that we have right here. So at first we kind of separated these into separate branches by themselves, but we can go ahead and just combine these guys. Let's go ahead and space this one out a little bit better. We have a 2 here, and so we can move this guy all the way over here. All right. And so this is going to be our tree. At first, I actually didn't know what the -1 meant because the instructions didn't say it. I ended up drawing a node like that. And when I looked at the example down below, it said that the 5 value was the root. And so I thought, okay, this is not possible. The root is -1 because why not have a negative value for a node? That's totally possible. They didn't even say all these values are going to be positive, and so I just assumed -1 was just another node. But I went over to the tests in Edabit, and I looked at another test case where a test came out to be the root, and so I noticed that okay, at that value, in the parent node, that similar index was a -1. With that said, that's going to be one of our strategies. How do we determine whether something is a root or not? Well, we can know just by that fact right there. The -1 automatically means that this is going to be the root. So how do we do this? How do we know? Or well, let's begin with also determining, okay, what is our function going to look like? We're going to get input values of the node. So we're going to get, these are going to be our inputs. We are going to get a row of nodes or an array of nodes. We're going to get the same array of parents. And then we're going to get one more value, which is going to be just a number. And they want you to tell us, is this value a node within this binary tree? Is it even there? If it is, what does it take? What characteristic is it? Is it the root? Is it the inner? Or is it a leaf? And they have a nice graph. They had a nice graph in the instructions where the root is the very top node. The leaf node is the very bottom ones that has no more children, and the inner are just everything in between. And so I believe the best way to go through this problem is to look at the indexes. Well, look at the indexes of the node that you're given as you iterate through the first one, and perhaps as you iterate through the second one at the same time. Remember, the parent and the node array and the parent array are the equal numbers. The node one is special in the fact that it does not have any, or it has only unique values. It's not going to duplicate the values, just like how we see 2 2s here and 2 5s, because a node can have 2 children, and so it might appear twice. And so what we're going to do is we're going to figure out, okay, does this guy exist at all? I think that would be the very easiest to do. We can iterate through the array, and as we're iterating through the array, we can say, okay, if we iterate through the array and we never triggered maybe a conditional that checked, am I in this node, am I in this node, as we go through the array, at the end of it, we can say, oh, I never met myself, therefore I'm not even here. Easy win right there. The node does not exist, so we got that taken care of. The next thing we can do is, as we iterate through that array, we can collect the indexes. Say we did find ourselves, we could break early if we wanted to, or we cannot. But the important part is, at that point where we meet ourselves and determine, okay, at least we're here, we're no longer the not exist case, we're still here, we can collect that index number. And we're going to use that index number to later look at the index within the parent array and say, for example, what I'm saying is, if our node was a 5 and we're looking for the 5, as we iterate through this, we capture the index of 0, 1, 2, 3, 4, 5, 6. So we capture the index of 6. And later we're going to say, okay, within the parent is the p of 6 a -1? And if it was, that means it's the root. And so there's another easy win right there. -1. And the other way to, and then the last thing, we have to determine whether it's a leaf node or a inner node. How do we do that? Well, if we iterated through the parent and it was never there, that means it wasn't a parent, and so that means it's the leaf node. And so we could actually do that as we iterate through the array for the first time, which is why I don't think we're going to end early, just in case, just so that we can see whether the node that we're looking for is within the parent one also. So first thing we're going to do, we're going to have one array, or we're going to have one for loop that iterates through the array. And as we jump in between here, we're going to check, okay, is it even here? If it is, collect that index so that later we can use that index to determine whether it is a root node or not. And while we were doing that, while we were jumping through this, we're actually going to jump through the parent array at the same time and determine, is it here or not? So another is exist case. Is it here or not? And if it's not there, then at the end of it, we can say, as long as it was at least in the node, we know this guy is going to be a child. And as long as it's not a root node, we're gonna know it's a leaf node. And so let's go ahead, take that strategy and write it in the code. All right, so now that we are here, let's go ahead over to the coding section. But one thing that I did want to nitpick at before, I also don't have the power to adjust these tests, but you know how I mentioned that I didn't know what the -1 meant? This is the example that I looked at in order to find it out, and the color scheme is very bad here. So let me see if, ooh, what the heck? Okay, maybe zooming in on it would help a little bit, but this is the example that I looked at, -3 as a node that we're given, and we're looking at the, the answer is going to be a root, and so I figured, okay, let's see what that 3 meant. This first array is going to be the array of nodes, and as you can see, the 3 is here, the index corresponding to it on the parent one is this -1, and so, like we know, everything here is a parent, but I noticed the 3 is the parent of the 2, the 3 here is the parent of the 4, that's good, it can have 2 children, but also this 3 is the parent of another number, which is pretty much, let's see, 1, 2, skip, it's also the parent of the 11 apparently, and that means that it has 3 children. Just the 3 appearing thrice here alone means that it has 3 children, and so, you know, I was not too happy with that because a binary tree, by definition, at most, has only 2 children, and so I believe that example is pretty bad, and hopefully someone fixes it. But anyways, let's go over to the coding. I wrote this down here. This is going to be our strategy. We check, okay, does it exist while we grab the index, and another thing that we needed to be doing is check the parent array to see if it's a root, or that's going to be after we go through the for loop, and is it in the parent array? If no, it's a leaf. And so this one probably goes ahead over here. But let's go ahead and edit this stuff. So like I said, npn, once you get to the function, you know, this is very bad. Talking about it within the instructions was fine, but I want to change these. And so we'll leave the capitalization of the nodes and parents there. What we want to do is we want to create some variables. We want to say does exist as one of our variables, and we're just going to default it to false. We also want to say, we also want the index, right? And we can just initialize that to nothing so far. We also want, maybe say in parent. I'm not sure about the in parent, whether we want to do it like that or not, but let's go ahead and do that for now. We're going to initialize our very simple for loop that's going to help us iterate through both the nodes and the parents array at the same time. So let's go ahead and say if, let's see, if nodes of I happens to meet this node, then we'll update our index. And what this means is as we're iterating through the array of nodes, if we grab the value, which is the value that we're looking for, well, that's our node, and so that's the index. The reason why we're grabbing the index is because we want to check the parent index later. And what we also want to do at the same time here is if parents of I is equal to this node, then in parent equals true. So we'll flip that. We'll flip that switch. And so let's go ahead and check, or let's write some conditionals for our returns now. And so if, let's see. And actually we should have also done a does exist. Does exist equals true. Flip that there. And so if does exist, or if it doesn't exist, then we could return the fact that it does not exist. So not exist. What the? Okay. So one thing that I added real quickly, hopefully you caught that. If I saw the node within here, we not only caught the index, but we acknowledged its existence, and so that's going to be from false to true. And so now if it does exist, then we return not exist. If it does exist, that means it's going to be either a root or a parent, or if it's going to be a root, leaf, or a inner. And so now we're at those three. We know it exists, so it's going to be root, inner, a leaf. And so let's go ahead and do the simplest check. Is it a parent or not? Parent of, let's see, we grab the index, and so let's do that. If parent of index is -1, that means return root. And what we did there was we got the index of the node within the nodes array. We know that its parent corresponds to the same index number in the parents array, and if that value itself right there happens to be a -1, we know that's a root. Therefore, we use that index that we collected and we check within the parent array, is it a -1? If it is, then it's a root. Now down here, last but not least, we check, is it a leaf node? And so the only thing we care about that is in parent. If in parent, whoa, what happened there? If in parent, okay, let's see. If it is in the parent, that means it's an inner node, because it is a parent. And so return, well, I don't know why it keeps doing that. Why does it keep going up to the top? Return inner leaf, I think that's what they wanted us to return. No, just inner. Okay, that's good. And at the very end, return leaf. So let's go ahead and double check this real quick. We created a couple of variables, does exist. We initialized it to false. We had the index over to nothing. We did in parent as false, and we went through the array. And actually, we don't technically need does exist. We can just check later here whether index is undefined or not. And so I would like to change that, get rid of an extra variable. And so if index is undefined, that means it doesn't exist. because we never assigned it. And at this stage, the index is undefined. It hasn't been defined yet. And so at the end of this for loop, if we never assigned it, it would be undefined, therefore it does not exist. That makes it a little bit clearer. At the same time, we caught the index. So if it wasn't there, we can now know, okay, we now not only know the index within a node, but we know its parent because the parent is the same correspondence index. And so we look in there, we check, okay, is it a parent or not? If it is, or if it is equal to -1, then we return root. Sounds good. We check, was it in the parent itself? So is it a parent? If it is a parent, that means it's inner. If it's not a parent, that means it's a leaf. And so I believe this checks. Let's go ahead and check it against this guy and see if we got any errors. All right, parent is not defined. Because I changed it to parents. So let's go ahead and change that. This guy, and I believe that's it. All right, there we go. That does it. And I know that if you look at the solutions, there are a lot more simpler solutions, like you use filters or something like that. That's totally a good way to do it. I believe that the only thing that this using a for loop has over that is the fact that you can do a couple things within the for loop. At the same time, iterating through the array twice, in terms of time complexity, it doesn't really affect it. It's like a 2 of n or something like that, which the constant doesn't matter anyways. And so I still like the for loop because it helps me explain things to you better. And so once you understand the strategy, maybe next time you can use those shorter methods or methods that make the code shorter. But anyways, I think this video is dragging a little bit. Thanks for watching, and if this helped you out, be sure to subscribe, check out the playlist for more. I am going to be building those up. If you see my comment in Edabit, please upvote it. I think that helps. And I'll catch you in the next one. Bye.